So, hello everyone. We are already on live. So, thank you so much for the presence today. Sabrina, we're going to talk about the chapters 4 and 5 of Dodelson's book. If I'm not wrong, it's about origin of species and inhomogeneities, right?
Yes.
Okay, so Sabrina, I will hand it over to you.
Okay. So thank you, Mateus. Hi, everyone. Today I'm gonna to present the chapter 4 and 5 of the Modern Cosmology books of Dodelson. So first, in chapter 4, for example, we're gonna talk about the early universe and about the non-equilibrium physics. This is the out of equilibrium physics phenomena. So the early universe, as we know, was dense and hot, and particles interacting with each other much more often than they do today, for example. The main interactions between particles keep the components of the universe in equilibrium. So in this chapter, we will see that the out of equilibrium phenomena played a role that was crucial to understand the formations of light element during the BBN, for example, the recombination of electrons and protons to form neutral hydrogen, and the production of dark matter in the early universe. So we're gonna see about some of these topics in the presentation of today. So we can study these phenomena, these out of equilibrium phenomena, using the Boltzmann equation in a homogeneous universe. So this equation helps us understand how particles were distributed in the early universe because of their interactions. So because scatterings happen very quickly, the particles of each type will follow the usual Bose-Einstein or Fermi-Dirac distribution, and all of them will share the same temperature. So this happened because the scattering process typically enforces the kinetic equilibrium. So we have here the Fermi-Dirac and the Bose-Einstein distribution, for example, and the behavior of the particles can be fully described by the temperature and the chemical potential as functions of the time. So this distribution here will depend on the energy and the chemical potential and the temperature, and this distribution here will depend too on the energy, chemical potential, and the temperature. So, for example, as we see here, in many cases, we are interested in situations where the temperature will be much smaller than the particle energy minus the chemical potential. So in this case, something interesting happens. The exponential terms here in the Bose-Einstein or in the Fermi-Dirac distributions will become very large. Because of that, we can ignore the plus or the minus one in the denominator. So this makes the equation much simpler. We don't need exactly to use the full quantum statistic anymore. Instead, the particle distribution will follow this classical Boltzmann distribution here, and which is a good approximation in this case when we are considering the gas like dilute. So the particles are not too close to each other in this case. So we can find a relation between this approximation and the density number of particles, for example. So this is important because the Boltzmann equation will be simplified in this case. So for example, this will be the Boltzmann equation simplified, and in this case, we have an ordinary differential equation for the number density of each type of particles that we are considering in this case. So we can always start with this equation when we are treating about abundance, about the abundance of the particles in the universe in this case. So this can help us to understand how the number density of particles will evolve with time as the universe expanding. So, okay. Another topic of this chapter was about the BBN, the Big Bang nucleosynthesis. So the out of equilibrium phenomena can lead us to the formations of the light elements in the early universe, and we call this Big Bang nucleosynthesis. It happened when the temperature of the universe is about 1 MeV. So this is the temperature of the universe cooled, for example. In this point, the cosmic plasma was made of relativistic particles like the photons, electrons, and the positrons, was made of the couplet particles like the neutrinos, and was made of non-relativistic particles like the baryons, for example. So what we want it is to determine the final nuclei formed by protons and neutrons, and we can try to estimate the abundance of this nucleus. So during the BBN, for example, when temperature was around 0.1 MeV, some light elements started to form, such as deuterium and helium, for example. So this is because as the temperature decreases, the high energy photons stopped destroying newly formed nucleus. This is, uh, but however, uh, heavier elements were not produced in this case. For example, we cannot have the reaction of helium 4 with a proton in this case. And this happened because we cannot have a stable nucleus with mass number 5. So, but we have this happen in stars, and this could happen because we have a very high density environment. And for example, we can have what we call a triple alpha process. That is this process here. Basically, it is a process where the helium 4 nuclei will interact to form a carbon nuclei. So we can have this process, for example, for a star, inside a star. And this will form an element that is have like carbon. So another topic that we can talk about in this chapter, it is about the neutron abundance. That is very important to understand the BBN. So we can measure, for example, the abundance of neutrons during the BBN by analyzing the time evolution of neutron-proton ratio, this ratio here. So at very high energy, for example, above 1 MeV, there are nearly equal number of protons and neutrons. That is, there are as many neutrons as protons. So, however, as the temperature drops below 1 MeV over the time, the neutron fraction starts to decrease. So, when the temperature will follows below 0.1 MeV, the neutrons and the protons will interact and will begin to form deuterium. So this reaction will mark the beginning of the nucleosynthesis. So we have here the graphic that will show the evolution of neutron to proton ratio. So, okay. Another topic about this chapter is about the light abundance, uh, the light element abundance. So we have here that the light element will be produced almost almost instantaneously at the temperature of 0.07 MeV. So, for example, the formations of deuterium in the universe does not happen immediately at the beginning because there are many energetic photons that break the deuterium in the beginning of the universe. But when temperature of the universe decreases, these photons start to lose energy, and deuterium is no longer easily destroyed. So, and then deuterium is start to react with protons. And from this, we begin to have the production of helium, for example. In addition, almost all neutrons that have this temperature here will have to form helium-4. So the final abundance it is given by a value that is 0.22%. This is a resulting in a high presence of light elements in the universe. But not all deuterium will be transformed into helium, for example. We can still, even today, measure deuterium in very cold clouds. So this will make the deuterium a powerful tool for the measuring the baryon density in this case for the universe. Since some of the reactions that form helium depend on the interaction between the deuterium and protons, and this will lead to a dependence on the baryon density at that time. So we can use the high redshift gas clouds to probe the baryon density, for example. So about the recombination, basically after the BBN, the universe is basically composed of protons, free electrons, the photons, the helium nuclei, and the heavy nuclei, for example. The next critical phase of the universe is the recombination. So the recombination will be a very important phase for the universe. It is basically when protons and neutrons combine to form neutral hydrogen atoms, for example. This process leads to the decoupling of photons because with the fear of free electrons, the electron will rate between photons and electron decrease, for example. We know that in the primordial universe, the electrons interacted strongly with photons. This is known as Compton scattering. But when temperature of the universe dropped the energy of photon, so this also decreased. So from this temperature here, that is next to 1 electron volt, for this temperature, the number of photons with enough energy to interact with electrons decreases. So the hydrogen that is formed is stopped being ionized by them, and neutral atoms begin to form in this scenario. So we have their recombination here in this case. So basically this was the chapter 4 of the Dodelson books that talks a little about these phenomena. And now we have the chapter 5 that we talk about the inhomogeneous universe, and we talk about a little about the matter and the radiation. So in this chapter, we are interested to understand about the anisotropies in the cosmic microwave of photons in the universe, for example, and the inhomogeneities in the matter that we have in the universe. So we have already seen how the number and density of species will evolve with time for a universe that is homogeneous. Now we want to understand the spatial and the directional dependence of the distribution function. So one thing we want is the evolution equation for the perturbations in the universe and how to describe the matter and photons in this given expanding spacetime with perturbations. So it's important to derive the Boltzmann equation for some particles like the photons, baryons, dark matter, and this is what we're gonna do in this chapter. So the Boltzmann equation for photons, for example, uh, we can do that. The first thing we can do is to write down the distribution functions for photon. But in this case, we are including a term that will allow a perturbation to the distribution function. So this term of the distribution function that is like a perturbation. It is represented by this theta here, that is a fractional temperature perturbation. So this term here will depend on the x, that is like a location, and will depend on the p, that is a direction. It's like the arrival directions of the photon. So we have here considering the inhomogeneities and the anisotropies in this case. So we can find a Boltzmann equation in terms of this theta here, of this perturbation. So that is given by this expression here. And it is important considering that with this equation, we can describe how the distribution function will evolve in the absence of collisions. That's why the name of this equation is collisionless equation, because we don't have here the term of collision. We call this to free streaming, for example. And this equation would take in account the gravitational effect of perturbations. But, however, this equation is not complete because for the first order in perturbation, we have a collision term that is not zero. So we have a Boltzmann equation for photons that have this collision term. So this is what we're gonna see here, for example, that for the photon distribution functions, we have a process that we need to take in account. That is the Compton scattering in this case. So we have a scattering process of interacting, that is the interacting between the electron and the photon, for example. And we can find an expression for the collision term that will depend on the fraction temperature perturbation that we see, the theta, in this case. So we can find this collision term in terms of this perturbation here, the theta, for example. And in this case, the Compton scattering will produce a photon distribution that it has only a non-vanishing monopole and dipole in this case. So there's a difference between the perturbation in radiation and in matter, for example. Perturbations in the CMB will remain small at all cosmological epochs, with, in another hand, the perturbations to matter are only small in the early universe. So they grow a lot and become nonlinear, and then they can form collapsed objects such as galaxies, for example. So we can equate this collision term here, this equation, with this collisionless equation here, and we can find, making a change of variables, for example, we can find a linear equation for the photons distribution that will explain how the distributions of photons will change with time, for example. That is very important to understand the evolutions of the photons with the expanding universe. So another equation that we have, it is the Boltzmann equation. In this case, we have the Boltzmann equation for dark matter. And it is important to understand that the evolutions of dark matter will play an important role in the growth of the structure through its gravitational effect, for example. So for understanding the evolutions of dark matter, the first step to find a Boltzmann equation, the first step is to find a Boltzmann equation that we can find in this case for two variables that I'm gonna talk here. So dark matter it is very important to we understand the structure formations. So because dark matter does not interact with any of the other constituents in the universe, we don't have collision terms. So we don't have collision terms for our Boltzmann equation for dark matter. And the cold dark matter will be non-relativistic. So we can use a Boltzmann equation collisionless for massive particles. So we treat dark matter as an effective fluid. So we need necessarily two variables for understand the evolution for the cold dark matter. That is the density perturbation, that is expressed by this delta here, and that is the velocity, this velocity here, of the fluid. This is not the velocity of the particles. Is the velocity of the fluid. So we can find two equations govern the evolutions of the density and the velocity of the cold dark matter that are represented by these differential equations. So this is our set of equations for cold dark matter that we are considering, that are fluid equation that we find integrating the Boltzmann equation. So as we did for cold dark matter, for example, for the Boltzmann equation for baryons, we have electron and nuclei that can be treated as non-relativistic fluid. And we only have to take the first two moments of their Boltzmann equations, as we did for dark matter, because it is non-relativistic. In this case, we take into account the zeroth moment and the first moment for these Boltzmann equations for the baryons. And it is the same thing for the neutrinos, but it is the same thing as was with the photons for the neutrinos, because we consider the neutrinos as being relativistic particles. So this chapter talks basically about this, and that's
So let's thank Sabrina. I will open for questions. People in the meet can also make questions if you wish. André says.
It was a good presentation, Sabrina.
Well, I maybe have one question.
Sabrina, can you hear Andres? He's speaking.
yes.
Can get close.
Yeah.
In the first part, you talk about the Big Bang nucleosynthesis.
Yes.
Is that theory have some limit for a point where it's invalid, or is valid for all the elements? Only works for some surface elements, or works for all the elements in the early table, for example.
I think that Big Bang nucleosynthesis, it talks most about the light elements in the universe, not the heavy, because is a process that can explain this epoch of the universe, where the universe was very early.
Okay.
It's a light nuclei.
Light nuclei.
Yeah, but you also have protons, neutrons. Works quite well with the observations, but we have some problems with the lithium. Lithium 7.
Yes, I was having that question also about the lithium. I heard that for lithium has some problems.
Yeah, perhaps lithium 6 and lithium 7, but there's a lot of uncertainties, statistical uncertainties on the measurements of the lithium abundance. So maybe some astrophysical problems. We do not know if it's a real problem or it's some astrophysical uncertainty, astrophysical source that of uncertainty. Maybe we don't know very well, but especially lithium 7 looks like there's a problem with the
Yes.
Okay, thank you.
I also have a question.
Yes.
When you show the Boltzmann equation, the first slide you show the Boltzmann equation. No, before of that, I wanted to thank you for the presentation. It's as Leticia said, it's a very good presentation. So congratulations for that.
Thank
Okay. So
It was, I think that it was here.
yeah. So you have a thermally average cross section, right?
Yes.
You know what is that? What means to have a thermally average cross section?
I know that we need to consider a cross section to consider the probability of the interactions because we are treating here with different particles in this case. So I think that is about this.
You know how to compute this thermally average? I
Um,
mean, you saw. I mean, not properly compute, but you saw some formula of how can you obtain of this thermally average cross section.
in the book, he makes this calculation, but I don't remember how. It's a big expression.
Okay, no problem. It's just to say that we saw this expression a lot of times when you are talking about Boltzmann equation. We can
Yeah.
think about weighted average, like in Portuguese we say média ponderada, right?
Hmm.
But instead, the weight you are going to consider in the denominator actually has to be with the thermal distribution, as you show. That in the case probably is considering since it's a cold dark matter, it's considering Boltzmann distribution, right?
Oh, okay.
So
Yes.
in the numerator, you have I mean, the weighted average is like a sum of all of your values with some weight, and you divide it for the denominator, right?
Yes.
So it's the same idea. You have a sum, but in this case, integral of the cross section times the velocity. The cross section depends on the interaction you are considering.
Yeah.
And in the denominator, you have this. I mean, you have the cross section, the velocity, and you have to put the weight. That's the Boltzmann the Boltzmann distribution, and you need to divide by the integral of the Boltzmann distribution. That's why it's a average.
Yes. Yes.
It,
Understood.
the thermal is because it's a thermal distribution. So that's what means thermally average cross section. It's the meaning of this expression.
Yes. Yes. Okay. Thank.
And another comment is that when you are considering some theories beyond standard model, sometimes you have a lot of interaction that you need to consider. For example, you have a dark matter that can be produced through, let's say, standard model particles, annihilation. You can have some Higgs decay. You can have a lot of process that lead to dark matter. So you need to consider every process in the calculation of the Boltzmann equation. So for each process, you have a thermal average cross section or a thermal decay width. So
See.
it's just a comment. I think that's an important comment to do about this Boltzmann equation. And other comment I wanted to make, I think we have time, is about the BBN. BBN is a very important era in cosmology because
Yes.
we have a lot of beyond standard model models in the early universe, but BBN put stringent bounds on this model. So each model you need to consider the BBN bounds. I mean,
Yes.
because sometimes you have a theory, you have a model, and this model overproduces some kind of particle that can disrupt the production of the light nuclei. So we need to consider it. I mean, this is a very important era that's important to put these bounds and these limits on the beyond standard model models, right?
Yes.
But I mean, it's just comments I'm making. And again, I want to congratulate you because of the very nice presentation. And I really wanted this layout. It's very beautiful.
Okay. Thank you.
Good presentation, Sabrina. I almost forgot to say.
So if there's no questions in meeting, I think no. So let's thank Sabrina again. I will end up the live stream.
Like and subscribe.
Oh, yeah. Thank you so much, and subscribe.